This is problem 14-127. Car A is traveling around a circular curve of radius 500 feet at a constant speed of 45 miles per hour, while car B is traveling around a circular curve of radius 750 feet at a constant speed of 60 miles per hour. Determine the velocity and acceleration that car A appears to have to an observer riding in and turning with car B at the instant shown. Okay, this probably seemed like a pretty complicated problem, and a couple instances it is compared to what we've been doing, but ultimately there is nothing different in the foundation of this problem compared to the previous problems that we have done. Okay, we're going to use the same two equations. We're going to calculate using the same terms, and all of the concepts that were in previous problems are here. It's just that now, basically, we don't have a origin that is non-moving, so that's one difference. And the thing that they're asking us to find is going to be a different term in both of these equations. So let's go to the math real quick, and I'll do a slight comparison with the previous problem with the rotating disk, and also point out exactly what the question is asking us to find. All right, so we basically have a car traveling, and it's traveling in a circular path, meaning the car itself is actually rotating as it travels. And same with the other car. The other car is going in a circular path, and the other car is technically rotating. All right, so the rotation may seem almost like irrelevant to a certain extent, depending on your perspective of these two cars turning, but they are non-zero values. The rotation of the cars are non-zero. All right, now, since we have two moving objects and both the objects are rotating, or what more importantly, at least one of the objects is rotating, then we can consider one of the objects to be our rotating frame of reference and the other object to be the moving thing. Okay, so just like when we had the disk with the slot and there's a slider moving along and the disk itself is rotating, okay, this slider is car A, and basically this disk is car B. Okay, and car B is moving and rotating. All right, now what does that mean? And since car B is moving and rotating, if we were to talk about slider A in the previous problem, now keep in mind, this is problems 14-117 to 120 type of example, where we had the velocity of A, we had to find like the slider, and then we had our origin being the middle of the disk, and that origin had a velocity of 0. This is not going to happen here. So if car B is our rotating disk now, our relative rotating axis, then that means that the velocity, the second term velocity, is going to be non-zero, right? So in other words, we're going to have a generic equation here. Velocity of A is equal to velocity B, which are actually the cars, A and B, plus the angular velocity crossed with the distance between cars A and B, all right, plus the velocity of A relative to the rotating axis. All right, so it's great. Duh, like this is the equation we've been using, big deal. Now, what's important is that now we have a car. I'll go with car A. What color was car A in the problem? Car A was the red car, so I'll use the same color as the book had. We had car A, and then we have car B. Okay, so the velocity of A is here. The velocity of B is here. These are how we see the cars moving at the locations that they are at, that their locations are located at this instant, this snapshot of the scene. This is the car's speed relative to the ground, velocity of A and velocity of B. Okay, now the car that we are asking to monitor the speed of or calculate the speed of relative to the other car is car A. Car A is what we are asking to, hey, tell me how fast car A looks like it's moving, or what kind of motion does car A have when you're sitting in car B, all right? Only looking at car A, not looking at the ground, just looking at car A. And then the fact that car B is moving is also something that car B is not taking into consideration. Car B is going to look at car A and is just gonna with their eye, and they're just gonna look and they're gonna see how A is moving relative to them. Well, okay, so that means that the omega cross R A relative to B, which omega is that? That is the rotation of car B. So I'm actually being a little bit confusing here. I should underline this in blue. So this is the rotation of car B, and then this is the distance of A relative to B. This could be either red or blue because it's just a value of their distance from each other. Okay, but the rotation is the rotation of the other object. Remember that this term in problems 117 to 120 was the rotation of the disk, the object that we were not calculating the ultimate velocity for. Okay, the slider was the v sub a in the problem. The disk was the v sub b, and this rotation was also the disk. Okay, so that means that technically all of this, and this being what I'm about to circle, all of that is the car B and also the disk. Okay, and this term. What is this term? Okay, this is the term that they are asking us to find. This is the velocity of A relative to the rotating axis. But in the disk problem, the rotating axis was stationary but spinning. This time, the rotating axis is rotating and also moving through space. Okay, so this term is the thing that the question is asking, the v sub a relative to the rotating object. All right. Okay, now hopefully it is clear what we know and what we're trying to find. And so now we can just start doing the math, right? Okay. Well, this is going to be a little tricky because we're going to have to deal with some dimensions. So I got to make some room here. There's going to be a lot of calculations. First, let's make sense of what is going on with the two cars. So there's going to be a radius of 500 feet given to us that car A is traveling around. And there's going to be a radius of 750 feet that car B is traveling around. And then these two cars at this instantaneous moment are going to have some distance between them. All right, so I'll label that D. And then they give us that there is a angle theta, and there's a known 30 degrees in the drawing. They don't explicitly talk about this in the explanation. They are just basically telling us that that is true in the diagram, but they don't point out. So make sure you're looking at your diagrams and what information is given in the diagrams when you're starting the problem. Okay, so that means that we can find some other dimensions. So one dimension would be, we can find using SOHCAHTOA. So try this out. 375 is the height of this line, all right? Which also means that this line is also 375 feet. Okay, so I just did the sine of the opposite over the hypotenuse at 30 degrees. Okay, and then you can do the opposite, sorry, you can do the adjacent of the hypotenuse and get the lengths of the bases of these two triangles, but the whole distance across is going to be, so from here to here is 1250. right? So you can play around with that. And there are now terms that we need to find for the equation. Okay, well, the velocity of B is given to us as being, well, 45 miles per hour, but we need to convert this to feet per second. So 45, I'm sorry, maybe I said velocity B, but I mean A. So velocity A is 45 miles per hour, which is also 66 feet per second. And then velocity B is 60 miles per hour and is equal to 88 feet per second. Okay, but these are magnitudes. So this is the magnitude of velocity A. This is the magnitude of velocity B. This is not sufficient for us to use in our equation. So the actual velocity A vector is going to be equal to 66 times sine and theta, all right, plus 30 degrees e hat x plus cosine theta plus 30 degrees e hat y. So you're probably thinking to yourself, wait, what? Why? Why is it theta plus 30 degrees? Okay, so I kind of like jumped ahead pretty far here on the logic, and let me explain why. So if we look at just the velocities, so if we have a velocity of car A with a angle of theta, so the velocity is that motion, and then that means that also the angle that this vector is at is theta in the vertical, because the theta in the horizontal for the position is a velocity perpendicular, so then it'll be theta in the vertical. We've seen this a few times. Hopefully that's not a surprise. Okay, so if I draw my x and y components, then this should just be that the velocity of A is the sine of theta and the cosine of theta for the I hat and j hat. Well, it is, but I didn't write I hat and j hat, did I? I wrote ex and ey hat. Well, why did I do that? Because in the end, we need to be able to add up the values with the same vector directions. So yes, it would be true that the velocity of A is actually equal to, and I'll write it out, 66 times sine, whatever theta is, and then that would be the I hat, and then plus cosine, whatever theta is, and that would be j hat. But when we do other calculation of the other terms, we're going to have ex and ey values. So what we're doing is a conversion. Well, how is this conversion working? So if I move this equation up a bit, and then draw the other vector. This is where one of these things I was talking about where things got a little complicated. Okay, so now we have a velocity B's position. So this was A, and now we're going to have B. And so B is moving at a different velocity. And remember, since B is the rotating object that is watching A, B is the disk in the earlier problems, but the disk wasn't traveling forward. But car B is rotating and traveling forward. And so the axis of orientation for the E hat X and the E hat Y are on car B. They're literally, the axis is on car B and will follow car B's orientation, which means that at this snapshot in time, car B is oriented 30 degrees. And we need to add this orientation onto the I hat and J hat version so that we can convert to an EX and EY version, which is where the plus 30 is coming from. I hope that makes sense. Okay, I know that's tricky. I know that can be a little complicated. Okay, so I have written technically the same thing up here with this I hat and J hat version, but by adding 30 degrees, because of the other car's orientation, now I have created my velocity A vector to be its vector position relative to the car B's orientation by adding the 30 degrees. Whew, okay, I'm sure that was probably a bit of a surprise and a little bit stressful for some of you. Don't worry, you are not alone. All right, let's just move forward and see how this continues to go along. So these values can be calculated though, because we can actually find theta. So theta is just going to be the inverse sine of 375 over 500 because of this triangle right here, okay? So theta is equal to the arcsine of 375 divided by 500, which is equal to 48.6 degrees. Okay, so that means we can actually calculate these values down here. The calculation ends up being 64.696 e hat x plus 13.057 e hat y. All right, that is the vector value for the velocity of A in the orientation of the rotating axis position. Whew, okay, all right. So now, velocity B. Well, velocity B will be a bit easier. Velocity B is moving in the lowercase y direction. This arrow is velocity B, and we have oriented the rotating axis on B. And so B will be traveling up the y at the 88 feet per second. So therefore, this is a much easier calculation. 88, and this will be just e hat y. That's it. Okay, and this goes to show that since we can draw velocity B in the e hat y, e hat x directions, that's why we need velocity A to also have those directions. We can't add I hat and j hat values to e hat x and e hat y values. Now, you might have been thinking, and I'm always trying to imagine what questions you might ask if we were in class. Well, what about that k hat? Why was there not an e hat k or an e hat z? Well, because this is a two-dimensional problem, and the k hat and the e hat z direction are the same thing, always. We can't rotate in the third dimension anyway. So therefore, the k and the e hat z are the same direction, and we didn't have to do any sort of conversion. So we were allowed to just have the k hat in the equations. Okay, so let's keep going. Now let's get the position of car A relative to car B. Well, how do we do that? The position is going to be this distance d that I had drawn there. All right. Well, how do we get that distance d? Well, you can do the SOHCAHTOA and find these two distances on the triangle. And then we know that these cars are traveling in a circular path, right? So car A and car B will eventually meet, and they'll actually meet right here. So that means that the total distance, where did I get the 1250? It's the 500 plus the 750. And then if you calculate the length of this triangle's length and that triangle's length, then you can subtract those two lengths from the total 1250. That is the 500 plus the 750. All right, try that out. I'll give you the answer. D is equal to 269.76 feet. Okay, so that's the answer. See if you can get that calculation. All right, that means that the distance of A relative to B, A is to the left of B, that means it's negative 269.76 feet in the I hat direction. All right, but we have to do the rotation of the fact that there is a 30-degree angle that is happening when we have the rotated axis here. Okay, so see if you can figure out the math of how you get the e hat x and e hat y directions when you're using a line that is in this position but is in that position relative to the x and y. So let me highlight this. I have a distance that is oriented horizontal, but I have a relative orientation for an axis at a 30-degree angle. That means that this line actually has a x, let me change my color one more time, has an x and y component. That was a little sloppy. Let me try that again. We have a y component for this red, and we have an x component of that red line. And we're going to have a 30-degree angle that we have to calculate. Okay, the vector answers are negative 233.6 e hat x and plus 134.9 e hat y. This is taking that horizontal line, D, between the two values, but projecting it on the rotated axis on B by 30 degrees. So that way the I hat turns into an EX and EY, because we need everything to be EX, EY, EX, EY, EX, EY. Okay? That is the reason and the method for doing that. All right, last thing is going to be, I'm running out of a little bit of space here, but it's going to be the omega crossed with R of A relative to B. Okay, well, we know these values. We are given that car B has a lever. I'm going to draw a new diagram of just B here. Car B has a distance of 750, a radial distance 750, and then has a velocity of a certain value. Okay, so if we are, and that certain value is 88 feet per second. Okay, to find omega, that rotation, omega r equals the linear velocity of b. Well, we don't know omega, but we do know the distance and we know the linear velocity. So we can solve for omega by dividing the radius over. Okay, so that ends up giving us a value of 0.117 radians per second. All right, so now that means that the omega here is going to be in the clockwise direction and in the k hat direction. So it's negative 0.117 k hat, all right, crossed with the vector that we found for r. We just found it here. So cross with negative 233.6 e hat x and plus 134.9 e hat y. Okay, all right. What does that do for us? Well, let's solve real quick, and then we'll just have a value. So 15.83 e hat x plus 27.41 e hat y is the answer to the omega cross r. So we have an answer. Let's go through. We have an answer for v sub a. We have an answer for v sub b. We have an answer for omega cross r. So therefore, check, check, check. And I told you that the question is asking us for the velocity of A relative to B. All right. The B is rotating and moving. So that's what that final term is asking. We have solved for all the others. We can just get the answer. So if you plug all these values in, they all are in terms of EX, EY. We can just add them all up. All right, so the answer for the velocity of A relative to the rotating object car B, the moving and rotating object car B, is 48 0.8, it's supposed to be an 8, 87 e hat x minus 102.35 e hat y. Okay, so there you go. That is the answer right here for the first part. They want us to find the velocity of car A as it appears from the person riding in car B. Halfway done. All right, final part is finding the acceleration.